Hello, everyone. Thank you for joining us today. I'm Sajun Etikadan, and I'm the marketing manager here at NanoSurf. Just a few ground rules before we get started. As we go along, if you have any questions, please send them through the Q&A tab on the lower portion of your screen. Please do not use the chat tab, since this makes it hard to keep track of the questions. We'll attempt to answer all of your questions towards the end of the session today. In case we do not get to your questions, we will get in touch with you directly. You can also reach us at info@nanosurf.com. This webinar will be recorded and will be available for future viewing on our website. So today's webinar is titled Nanomechanical Measurements, Understanding When to Use an AFM or a Nanoindenter. Our presenter today is Dr. Dalia Eblon. Dalia is the founder of SurfaceCar, an AFM and nanoindentation-based measurement consulting and training company in Greater Boston area. Dalia has over 20 years of experience in nanomechanical characterization methods. Dalia also serves as a technical co-chair of the Nanotech Conference, part of the Tech Connect World. She holds an AB in chemistry from Harvard and a PhD in physical chemistry from Columbia University. With that, let me go ahead and turn things over to Dalia. Dalia?
Good morning or good afternoon, maybe even good evening to everyone. Hope everyone and your families are healthy and well. Before I dive into this topic of which instrument to use, I would like to just briefly review what are the kind of nanomechanical measurements that each instrument can do. So AFM can measure a wide variety of mechanical properties. The ones that we're going to focus on today are the modulus or stiffness and adhesion, but it can also measure properties like friction and also dynamic measurements like storage modulus, loss modulus, and loss tangent. And there's basically an alphabet soup variety of modes one can operate the AFM in order to measure these different properties. And the focus for today's webinar is going to be on force spectroscopy, or it's also called static force curves to measure modulus and adhesion. Now, an instrumented nanoindenter can also measure a wide variety of mechanical properties. The ones we're going to focus on today are hardness and elastic modulus, which is the stiffness. And that is done through what are called quasi-static indents. But the nanoindenter can measure other properties such as creep, fracture toughness. You can add a second dimension to the indenter and perform nano scratching measurements to measure the coefficient of friction and scratch resistance. And like AFM, it can also measure dynamic measurements. So storage modulus, again, loss modulus, and loss tangent. Now, just to briefly go over the operating schematics for each instrument, because they're actually very different from one another, even though, we're using them to probe very similar mechanical properties, or even the identical mechanical properties. So for the AFM, which I think most of the people calling in are familiar with, right? We have a very small cantilever with a small tip hanging off the end that's going to interact with the sample in a variety of ways. And then we have a laser reflected off the back end of the cantilever that's directed towards a position-sensitive detector to track the motion of this cantilever as it interacts with the sample. Now, when it interacts with the sample, it can twist, it can move up and down, it can move laterally, a lot of different ways this cantilever can move. And we track both the sideways and up-down motion with this laser. Now, the instrumented nanoindenter actually behaves in a very different way. It's basically a diamond tip that is just going to plow in and out of the sample in a very simple motion, certainly simple relative to what the AFM cantilever is doing. So for example, here, all it's going to do is going to poke into the sample and then pull out and leave an indent in there, depending on the load. So very different behaviors between the nanoindenter motion and then the AFM cantilever motion. So let's just start with terminology. AFM is sometimes called a nanoindenter. This is confusing and not very helpful. The source of this confusion comes from the ability of both techniques to conduct the force curve measurements that are the subject of today's webinar. So they can both do them, and that's why sometimes AFM, I have heard, been called a nanoindenter. I certainly try and avoid that kind of terminology. And so from here forward in this webinar, when I talk about a nanoindenter, I'm referring to an instrumented nanoindenter only, which is this guy here. This is the instrumented nanoindenter, where we've got our diamond tip that has confined motion in Z to just go up and down. And the main purpose of a nanoindenter is nanoindentation. So when I say nanoindenter, that's what I'm referring to. The AFM is typically using a silicon tip on a cantilever. And the big differential here is that the Z motion is not confined to up down. In fact, the cantilever has multiple degrees of freedom. Like I had mentioned, it can twist, it can turn, move sideways. And we actually take advantage of that for many imaging modes, but for nanoindentation, that's actually not ideal. But the main purpose of the AFM is actually to image and to conduct individual property measurements and mapping. And here's just a little SEM image of a diamond nanoindenter tip and our well-known AFM tip and cantilever. And so the focus of this webinar today is really to focus on only one kind of measurement that each technique can do, is force curve-based measurements, and try and understand, the pros and cons and what is the suitability of the different techniques for different applications. All right, so let's review what these static force curves are. Big picture, they're simply poking the sample. You're poking the sample, you're going in and out with either your cantilever or your diamond tip. So let's explore what it is for the AFM first. And by the way, while you're poking, you're measuring the force and the displacement into the sample of either your tip, your cantilever tip, or your nanoindenter tip. So let's explore what it is for the AFM. So for AFM now, we have obviously force here on the y-axis, and then tip sample indentation here on the x-axis. As we come in from the right, we approach the surface, and then we're going to get very close, and we're going to get a snap in of the cantilever into the sample. Now we're in contact with the sample. So now we're going to push against the sample in what's called the repulsive regime. And then we withdraw, so we reverse. And as we pull out, especially if the sample is very sticky, the tip will get somewhat stuck in that sample until you pull out with enough distance that it finally pulls out here, and then you leave the sample. And so actually there's a lot of information in this curve. First, notice the hysteresis between the approach and retract. There's a lot of information in that. There's a lot of information here for the adhesion portion of your sample. There's information in this hysteresis here for dissipation and viscoelasticity of your sample. This portion here, typically, depending on what model you use, it will dictate what portion you use, will give us the stiffness or modulus. But this is a kind of force curve that we measure for AFM. And again, the cantilever deflection is convoluted into this measurement, the cantilever deflection with all its degrees of freedom. The analog force curve for nanoindentation looks like this. So this is now a load versus displacement curve here. And so typically what you do in a nanoindentation measurement is you push in with your diamond tip. You typically will hold at the maximum depth just to give the piezo a little bit of time to settle down, and then you unload or withdraw. And so here from this initial unloading portion, we're going to measure the slope and get the stiffness or modulus. You can also get information from the hysteresis between your loading and unloading portion of the curve as well. But again, it's the straight up-down motion of the transducer enables a much more straightforward measurement of your displacement. But these are the hearts of the various measurements that we're going to be discussing today. Okay, So now that we have a bit of a background on what the measurement is, now the question is, when would I use AFM or nanoindenter for these force curve type measurements? And I like to boil it down into 4 considerations. And we're going to go through each one of them step by step. First, what kind of properties are you trying to measure? Second, what kind of sample are you measuring? Third, what resolution do you require? And finally, do you need to image your sample prior to force curve measurements? All right, so we're going to start with the first question. What kind of properties do you want to measure? And for that, I want to draw your attention to this graph here on the right, where we're looking at a stress strain curve to understand what the elastic and plastic regime is. So this is a stress strain curve for a model crystalline uniaxial material. And you can see initially when you pull on it, and stress strain has a linear relationship. It's in blue. That's called our elastic region. That slope or proportionality constant is actually the modulus. As you keep pulling, you enter a nonlinear regime between stress and strain. That's our plastic regime. And then finally, we fracture or break the material. So AFM measures elastic properties in the elastic regime. This is also referred to as recoverable or non-permanent reversible deformation. Nanoindentation can measure both elastic and plastic properties, where the plastic regime is where you have permanent deformation. So some plastic properties you may be familiar with are properties such as yielding, ductility, or toughness, and hardness, which is the resistance to localized plastic deformation, is the one that the nanoindenter measures, in addition to the elastic properties that it can also measure. Both techniques do measure rate-dependent properties, which are the viscoelastic properties, such as the storage modulus, the loss modulus, or the loss tangent, which is the ratio of the two. And this is particularly useful for materials like polymers, which are very viscoelastic. All right, so our second question is, what kind of sample are you measuring? So generally, AFM is better for softer samples, where a general rule of thumb that I like to use is about a gigapascal or lower. And so the kinds of materials that corresponds to are polymers that are a gigapascal or lower, biological materials, hydrogels, some very sticky materials that also tend to be soft. And this is limited by the spring constant of the cantilever in terms of getting a decent sensitivity, but also to be able to deform the material. Nanoindentation works for the other end of the modulus, where it really excels for stiffer materials with very high modulus, materials such as ceramics, metals, stiff polymers, and semiconductors. And so here I have a chart of just some materials where we've got their modulus listed here. And so you can see on the low end of modulus, we've got hydrogels and elastomers like a nitrile rubber. Those would be wholly appropriate for AFM. Then this next group here, we've got thermoplastic polymers and polystyrene. Those are kind of in the middle and would probably be appropriate for both techniques. And then we've got some metals here with very high moduli, which are really only appropriate for nanoindentation. And in general, these guidelines are also deriving from the forces used by each technique. And I really want to hammer home that they are operating in different force regimes, right? The AFM is very low force of piconewton to nanonewton, and the nanoindenter is higher force in the micronewton to millinewton regime. All right, our third question is, what kind of resolution do you require? And we have to think both about lateral resolution as well as resolution in Z or height. So lateral resolution, the diamond tip of the nanoindenter has typically greater than 100 nanometer resolution. It's not great compared to the AFM tip, which has 10 nanometer resolution. Z resolution, or in thickness and height, again, the AFM has significantly higher resolution than the nanoindenter. So nanoindenter can typically indent down to a few nanometers comfortably, whereas the AFM can do much less than that. This also comes into play for thin film applications. So with thin films, we have this additional constraint of what's called the 10% rule, where you don't want to be indenting more than 10% of your film thickness, otherwise you're going to be feeling the substrate underneath. So in general, for thin films, depending on how thin they are, you might be limited by the Z resolution. Another way you can think about resolution is in terms of volume. And you can see here how the AFM can probe much smaller volumes than the nanoindenter. It really is a higher resolution technique. So here, what I want to show is this is a nanoindenter tip, and there's a cantilever, and hanging off of there is a tip. And you can see how much bigger, the relative scales here between your nanoindenter tip and your AFM tip are. Again, AFM tip is much higher resolution. And here also is an image of a sample that a customer had brought to me that they wanted me to make measurements on, force curve measurements on. And you can see some of these particles are only a few tens of nanometers wide. Would simply be impossible for a nanoindenter to probe them, but certainly very appropriate for the AFM. And these resolution guidelines, again, they're governed by the forces used by each technique. So again, I remind you, AFM is a much smaller force range than the nanoindenter. Now, often these high resolution measurements, if you need high resolution, it's coupled to image to find the feature or area of interest. Actually, this image here being a prime example. I need to be able to collect a high resolution image here in order to find these particles and then be able to probe them. So that brings us to our final question, which is, do you need to image your sample first to find the area of interest? So many nanoindenters don't have an imaging capability, but if they do, it at best contains a poor man's AFM, where it can only do a form of contact mode imaging with 100 nanometer plus resolution, so very poor resolution. So, and the image, if you do need to image and find, AFM definitely has superior capabilities because you can image with higher resolution. You can also image soft materials, right? Contact mode will chew up soft materials like biological samples and certainly polymer samples. AFM has different modes to handle such materials. And the other advantage is AFM can image materials with other channels other than topography to find interesting regions of interest that you may not observe in the classic height channel that you get from something like contact mode. So here I show a topography image of a polymer blend. This is a corresponding phase image. And you can see in the phase image, there are all these different domains. I got this bright white domain, this yellow domain, kind of dark brown or orange here. And what I can do is through the phase image, I can pick these different areas to do my force curves in. Especially if I wanted to focus in on, for example, the white domain, which is one of the components in here, very easy to do that through the phase image and impossible to do through the topography image because you simply don't have the contrast to do it there. So these other channels for looking for your features or areas of interest is available to you through the AFM, and then you can do this point and shoot, to select what area you want to do on the force curve for the force curve, which you don't have access to with the nanoindenter. Like I said, the nanoindenter, you can only do low res contact mode imaging of topography. Okay. So a word about the models we use for force curves. So no matter what instrument you use, whether it's the AFM or nanoindenter, all the force curves that you collect are modeled with contact mechanics models in order to extract that modulus or stiffness information. And I will be honest, there are times that the model simply is not a good fit for the sample. And in that case, you're a little bit stuck because these are the models that are available to us. But it is something to be aware that the modulus is only as good as the model fit is to your data. So nanoindentation is modeled by Hertzian mechanics, shown here, developed in the 1880s by Heinrich Hertz, where you take two simple spheres and you press them together, and he calculated the contact area and depths that result from that. AFM force curves can be modeled by Hertzian mechanics if your tip and sample, if there's no adhesion between them, or by models that do include adhesion. And those models are DMT and JKR, which are appropriate for polymer and sticky materials. I also want to say a word about calibrations for these nanomechanical measurements. So the main calibration that is required is the tip shape calibration for both techniques. And the nanoindenter has a very well-established protocol to calibrate tip shape on a reference sample at a series of depths. And that is done through what's known as the Oliver-Farr method. For AFM, you also have to do a tip shape. You also have to do tip calibration. And that you can do via direct reverse imaging. Like I said, we have to do, but I will be very honest, it's not as accurate as a nanoindenter tip calibration. And so one thing that's been done to address this in the tip manufacturer community over the past year are calibrated spherical tips that they are now developing that look like this, where you actually have this little sphere on the end of your tip. So now we have a well-known geometry, a sphere, as well as radius, at least at the outset when we're imaging. And that's been a really big help in this issue of tip shape calibration. You kind of don't have to worry about it. What you do have to worry about is if the tip shape changes as a function of wear or contamination during the course of the experiment. So that problem has still not gone away. And in addition to tip shape, you have to calibrate the spring constant and the deflection sensitivity, which are kind of standard for all nanomechanical measurements with AFM. Okay, so now that I've kind of outlined, some of the thought process that goes through in terms of determining one or another, I just wanted to go through some applications where you can see how they're used for different materials and different measurements. So the first is an instrumented nanoindenter measuring the properties of lubricant boundary films. So these are about 100 nanometer inorganic films on a stainless steel substrate. They're about 100 gigapascals. That's really, that's on the stiff side. Obviously not appropriate for the AFM. We had to go with an instrumented nanoindenter for this. And so here's an image of the boundary film, and you can see our little indents. Wanted to make sure they're well placed and don't interfere with one another. And then a sample indent. And so we looked at the modulus and hardness, right? We wanted to probe the elastic and plastic properties of these films as a function of the chemistry of these films. So we looked at different lubricant compositions and tried to probe their modulus. So that's what these colored points are the different lubes. And the black points are the underlying steel substrate. And this is a function of depth. And you can see pretty clearly that even already at 15% here of the film depth, we were approaching the substrate values. That's that 10% rule I've been talking about. So again, looking at the modulus and hardness of these lubricant boundary films as a function of the chemistry of the lubricant. Here is another example of nanoindentation measurements on sugar crystals. So here you can see the loading, unloading portion. There's a little bit of a hold up there. And I just want to call your attention to the load. So this is a 100 micronewton load, because we're in the micronewton regime, and we go in about 38 nanometers of displacement, which is, not trivial for 100 micronewton. And you can see what's called this pop-in event as the crystal fractures here. Then we went to 1,000 micronewton load. Now we're going in at 236 nanometers into our sample, and now we can see a lot of different pop-in events as we poke further into this crystal. And then here is an example of a series of 100 micronewton force curves, indentation curves, force curves, with pretty nice repeatability among them. I'm switching to some AFM measurements. This is one of my favorite examples of how to take advantage of force curves. It's one of my teaching examples in my courses. And here what we have is we have a 3.5 by 3.5 micron image of a blend of polypropylene here in the background that has been impregnated with these rubber domains that are only a few hundred nanometers big. And so we use an AFM to image this. Imaging this in contact mode is actually very difficult because the rubber would smear. So you really need to image it in a gentler tapping mode technique. And then once we do that, we can point and shoot, just focus in on different areas to collect our force curves. So the force curve on the polypropylene is shown in black, and the force curve on the rubber is shown in red. And you can see, certainly qualitatively, very significant differences between the force curves on these two materials. First off, much steeper slope here on the retract than on this guy. A lot more adhesion on the rubber than on the polypropylene. A lot more hysteresis. It's due to the viscoelasticity in the rubber. And so qualitatively, you can see big differences. And then once you apply the models, you can really start to make quantitative measurements on the modulus and adhesion to differentiate between these two samples, these two components, in the sample. So this is just these single point measurements, but with an AFM, you can build a force map. And so this is a map now where you do a force curve over the whole area of the same kind of material. So this is showing the height channel and now the adhesion channel. We put out the adhesion of every force curve. And this is where you see dark here in the height. That's our rubber domain. You can see that's corresponding to much higher adhesion than the polypropylene. That makes a lot of sense. And then we can also fit with the appropriate model to get at the modulus, the correct modulus. So here I've chosen to use the JKR model because that is really what's appropriate for the rubber. So when I use a JKR model, I can see that the rubber has a much lower modulus than the surrounding polypropylene. And here's another rubber domain, here's another rubber domain, and here's another one. Okay, so that's good. And now when we actually make the measurement, we can see that the JKR modulus for the rubber is 8 megapascals, which is about right. But the JKR modulus for polypropylene is actually off. It's very low, should be around 1.5 to 2 gigapascals. And the reason that it's off is twofold. First, the JKR model is actually not appropriate for the polypropylene. The DMT model is more appropriate. And also, I had chosen a spring constant for a cantilever that was really optimized for the soft rubber domain as opposed to the polypropylene. And this is an issue you run into very often, especially if you're looking at a sample that's very heterogeneous with a very wide range of mechanical properties, the AFM force curves. It can be hard to find one cantilever that suits all the different materials in your components. Sometimes you have to optimize for one or the other. But again, this also shows the limitation of the models. Here's another example where we looked at 2 rubbers that had been cured for a different amount of time. So when you cure a rubber, it should stiffen and become less adhesive. And so the first rubber, this is just a force map and it was homogeneous. There are no other components, not a multi-component blend or anything. And so we look at the modulus adhesion and get a histogram of the values and understand what their modulus and adhesion values are. And then the second rubber, which had been significantly cured, we can now measure again the modulus and adhesion, and we can see a stiffening and also less sticky. The rubber has become stiffer and less sticky than the first one. Biological measurements are where AFM can really excel at and really provide a unique tool to make measurements that are not otherwise available. And this is an example of making force maps on epithelial cells, where they looked at the adhesion and the elastic modulus on the cell. And you can see on the cell kind of a range with the modulus. You can plot up in the histogram and quantify the modulus on the different regions. And again, these kinds of measurements are really uniquely possible with AFM. Hydrogels, very soft. Oh, let me just stress, look at the moduli that we're measuring here, right? So we're kilopascal range. Again, soft materials appropriate for AFM. Just want to also stress again here, these rubbers, low megapascal region. Again, what's appropriate, more in the AFM regime of operation. Hydrogels. This one is measuring at 5 and 24 kilopascals, where you can again create force maps and measure different samples and average them together, and you can get accurate moduli of these very, very soft hydrogels that otherwise are impossible to measure on this length scale. And then a final example is a polymer brush. This is polybutyl acrylate. And so here you have a height map. And then this was force curve based measurements, and you pull out the adhesion and the modulus at each point. And then you can quantify the different properties of, so here's the modulus, here's the adhesion, and you can quantify these properties for these different components in this polymer brush. Okay, so just a couple of slides summarizing what we've discussed. There are things that both techniques can do and do very well. Both can handle fluidic environments, and both have the ability to do measurements as a function of temperature. So both of them have similar environmental capabilities that are really key, differentiators from perhaps other vacuum-based techniques. Both nanoindenter and AFM can handle a different kind of environments. Also, they can both handle single point or mapping measurements. The mapping measurements do tend to be slow for both techniques. Actually, even for nanoindenters, even a single point measurement tends to be slow because you need to give the piezo time to stabilize for every single measurement. But AFM is developing techniques, manufacturers are developing techniques for more rapid force curve acquisition at this point, so that you can even do it in real time. But these can be very slow measurements, so they will take time. What are some of the advantages of nanoindentation? So it can probe both elastic and plastic properties. It can probe elastic properties even with plastic deformation through the initial part of the unloading portion of the curve. Nanoindentation has very well-established protocols to calibrate tip shape. It is highly automated for statistics. So I just said that, it is a slow measurement, and it really is. However, the good thing is that the instrument vendors have worked very hard at automating measurements so that you can run them for a long time to build up a good number of loading unloading curves for analysis. Another huge advantage, it has confined motion in the vertical axis. There's no cantilever bending or deflection, which makes it a much more straightforward measurement. And as a reminder, the load regime is micronewtons to millinewtons. Advantages of AFM. So first, we have higher resolution laterally and in Z than nanoindentation. It has superior imaging capabilities, right? So higher resolution, it has modes with materials-based contrast that you can tap into to probe the different components, and has a really good ability to find features or domains of interest. It also has the ability to handle softer samples, including biological samples, and again, a much lower force regime than the nanoindenter. And so finally, it's my final slide, just to kind of summarize the 4 questions that I had laid out in the beginning. When to use an AFM or nanoindenter. What kind of properties are you trying to measure? If you need plastic properties, you're going to need nanoindentation. Elastic properties, you can use either one. What kind of sample are you measuring? AFM can handle softer and stickier materials than a nanoindenter. What resolution do you need? AFM has higher resolution in X, Y, and Z than the nanoindenter. And do you need to image your sample prior to force curve measurements? AFM has superior imaging capabilities, and some nanoindenters even don't have any, so you just have to go by what there is optically. So I hope I've been able to shed some light, at least to my thought process, on which instrument to use, and I will be happy to take any questions.